Hello, so this is a revision video for IB Chemistry S1.3.5 Electron Configurations. Within sublevels or subshells, electrons can only exist in certain regions of space. These regions of space are called orbitals. An orbital holds up to 2 electrons and they must have opposite spins, shown as arrows pointing in opposite directions. Electron configurations are used to show which orbitals are occupied in a given atom or ion, and how many electrons are in each. There are 3 key rules that we use for assigning electron configurations: the Aufbau principle, Hund's rule, and the Pauli exclusion principle. The Aufbau principle tells us that electrons will fill the lowest available energy orbitals first in a given shell. So the general fill-in order for subshells in an atom to an atomic number of 36 is the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p. Notice that 4s is filled before 3d. Hund's rule tells us that when electrons fill orbitals of equal energy, they go into separate orbitals first with parallel spins. This reduces electron repulsion and increases stability. In other words, all the orbitals in a given sublevel will be singly filled before electrons pair up. Pauli's exclusion principle tells us that no 2 electrons in the same orbital can have the same spin. One must be spin up and one must be spin down. In other words, one atomic orbital can only hold a maximum of 2 electrons, each with opposite spin. When writing electron configurations, we use a standard notation. The notation uses a number for the main energy level, N, a letter for the subshell, for example SP or D, and a superscript for the number of electrons in that given sublevel. Inner or core electron configurations can be represented using noble gas shorthand notation. For example, the first 10 electrons in an atom can be represented using square brackets Ne, which signifies 1s2, 2s2, 2p6. We can also write electron configurations for charged ions. For positively charged ions, we remove electrons from the highest energy level in a neutral atom of the element. For transition metals, we remove 4s electrons before 3d electrons. For an example, an Fe2+ ion would have an electron configuration of square brackets Ar 3d6. This is because the electron configuration for a neutral atom of Fe would be square brackets Ar 4s2 3d6. We remove the 4s electrons first, and because it's a 2+ ion, 2 electrons need to be removed, which would leave us with an electron configuration of square brackets Ar 3d6. These are all just general rules, however, and there are some exceptions. 2 important exceptions to memorize and know at this level are chromium and copper. Chromium has an expected electron configuration of Ar 4s2 3d4. But the actual electron configuration is Ar 4s1 3d5. Copper has an expected electron configuration of Ar 4s2 3d9, but the actual electron configuration is Ar 4s1 3d10. The chromium and copper exceptions occur due to the added stability of half-filled and fully filled d orbitals. Arrow in-box diagrams can be used to show how orbitals are filled and their relative energies. Each box signifies 1 orbital, and each arrow 1 electron in the orbital.